This is part 2 of the Chapter 9 review, and we're going to begin with problem 10. In problems 10 and 11, we're dealing with the right triangle similarity theorem, which tells us that if we draw an altitude from the right angle of a right triangle to the hypotenuse, it creates 3 similar triangles. So you can see we have one triangle here, a middle-sized triangle here, and the big triangle, and all 3 of those triangles are similar. That is, all the corresponding side lengths are proportional and the corresponding angles are congruent. Now the first part of the question says identify the similar triangles. So in number 10, what our job is to list a similarity statement that labels all 3 similar triangles. Now I'm going to start with the biggest one. And it's, from my perspective, it's easiest to start with the most identifiable angle, which is the right angle. So I'm going to start with triangle F, and I'm just going to move down to G. I'm going to go in a clockwise fashion. So F, G, E is similar to triangle. Now, I'm going to use this middle-sized triangle. I have to pick an angle that is a right angle. So that would be this vertex. So that would be triangle H. Then I have to have the vertex in this triangle that corresponds to this vertex, G, in the big one, which happens to be G because that angle is shared between the middle-sized triangle and the big triangle. So that's HG. And then the remaining vertex is F, which is similar to triangle. Again, in the little one, I'm going to go with the right angle because that corresponds to these. So that's triangle H. I have to go to the vertex that corresponds to angle G, and that happens to be this one. And the reason it can't be this one is because E is shared with the big triangle. So E is going to correspond to E in the big triangle. Therefore, it's H, F, E. And if you work in this fashion, in this methodical fashion, you shouldn't have any real problem identifying the corresponding sides. But if you try to do it in a haphazard fashion, it's going to be a little difficult. Now, we have to find side X. Now to find X, we could use the geometric mean altitude theorem, but I want to show you how to do it without the geometric mean altitude theorem, just using the similarity statement, and then contrast that with the geometric mean altitude theorem to show you the value of geometric mean altitude. So I need X. So as usual, I like to put my variables in the upper left of my proportion. And X is HG. And I'm going to use the big triangle and the small triangle. I'm sorry, the middle triangle and the small triangle. That means this triangle and this one. And I'm underlining them just so that I know where I'm going. So HG corresponds to HF. So HF is 9. And then I go back to my middle-sized triangle, and I have 9 here. That's the only other side in this triangle that I know about. And HF in my middle-sized triangle corresponds to HE in my little triangle. So HE is 6. And now I just work this through. X equals 9 times 9 divided by 6, which is 13.5. Now, as it turns out, by doing this relationship the way we did, we actually did use the geometric mean altitude theorem, because the geometric mean altitude theorem says the altitude is the geometric mean because these are the means of the proportion and they're the same value. This 9 and 9 become the geometric mean, and the altitude is the geometric mean of the 2 segments on the hypotenuse. So the two segments on the hypotenuse are 6 and x. So in this particular case, the way we worked it using the similarity statement was no different than working it with the geometric mean altitude theorem. So now let's work problem 11, but this time we'll just go ahead and use the geometric mean altitude theorem. So for 11, we know that it's a geometric mean problem, so we set up a proportion like we would the geometric mean, and x is the geometric mean because x is the altitude. The geometric mean always goes in this position, and the other two segments go in the other two open positions, and it doesn't matter which. 4 could go here, 6 could go here, it doesn't really matter. 6 times 4 equals x squared. The square root of 6 times 4 equals x. So before we write down our value, we have to simplify this. We have the square root of 24. First prime number is 2, goes in 12 times. 2 goes in 6, 2 and 3. So one pair of 2's comes out. That's 2 square roots of 6. So we know x equals 2 square roots of 6, which is approximately 4.9. But again, the exact value is 2 square roots of 6. So let's go ahead and move on to problem 12. In problem 12, we have a leg that we're looking for, and we have the segments on the hypotenuse. So that's this key signature to the geometric mean leg theorem. So that's what we're going to do here. And in the geometric mean leg theorem, the leg is the geometric mean of the entire hypotenuse, 9, and the segment on the hypotenuse closest to the leg, 3. So we have x squared equals 27. Take the square root of both sides. X equals the square root of 27. And 2 doesn't go into that. 3 goes in 9 times. 3 goes in 3 times. So x equals, there's one pair of 3's, 3 square roots of 3, which is approximately 5.2. All right, let's look at problem 13. Here again, we're given a leg, and the entire hypotenuse this time is what we're looking for, and we have the other segment, which is 16. So this looks like another geometric mean leg theorem. So 13, set up the geometric mean, and the leg is the geometric mean. Geometric mean always goes in the second, third proportional positions, and that is to the entire hypotenuse and the segment closest to the leg, 16. So now that's all we have to do is multiply both sides by 20, and x equals 20 times 20 over 16, which is 25. All right, let's move on to problem 14. In problems 14 through 16, we're asked to find the geometric mean. It's kind of interesting that they would put the review for the geometric mean after we've used it in the geometric mean leg and altitude theorems, but nonetheless, here we are. And let's work problem 14. We're looking for the geometric mean between 9 and 25. We don't know what it is, so the geometric mean is our value, our variable. That goes there. 9 and 25 go in the remaining positions. So x squared equals 25 times 9. X equals the square root of 25 times 9. That makes x equal to 15. Now to problem 15. Again, we're looking for the geometric mean. So we set it up in the same way. X is still the geometric mean because we don't know it. 36, 48 are the other two numbers. X squared equals 36 times 48. X equals the square root of 36 times 48. So that's the square root of 1728. 2 goes in 864 times. 2 goes into that, 432. 2 goes in 216. 2 and 108. 2 and 54. I'm going to have to go over here now. 2 goes into 54 27 times. Then it doesn't go in again, so the next prime number is 3. 3 goes in 9 times, and we have 3 and 3. So we have 1 pair of 2's, 2 pair of 2's, 3 pair of 2's, and 1 pair of 3's. So that's 2 times 2 times 2 times 3, square roots of 3. That's 8 times 3, which is 24 square roots of 3. So that's the exact value, and that's approximately equal to 41.6. So now let's go on to problem 16. Again, we have two different numbers. We don't know the geometric mean, so that's 12 and 42. X squared equals 12 times 42. X equals the square root of 504. 2 goes in 252 times. 2 goes in 126. 2 goes in 63 times. 2 doesn't go into that. 3 goes in 21 times. And 3 goes in 7 times. So we have 1 pair of 2's and 1 pair of 3's. So that's 2 times 3, which is 6, square roots of 14. So that's 2 times 3, square roots of 2 times 7, which is 14. 6 square roots of 14, which is approximately 22.4. These are the exact values here. Alright, let's move on to problem 17. These problems are asking us to find the tangents of the acute angles in the right triangles. Write the answer as a fraction and a decimal rounded to 4 places. Before we get into this, I want to recap real quick the idea behind sine, cos, and tan and the limerick that we used in class to solve these problems. In any right triangle with a given angle, we pick this angle just for reference. The side opposite is labeled O, the side adjacent to the angle is labeled A, and the hypotenuse is always H. The sine function gives us the ratio of the opposite over the hypotenuse. Cosine is adjacent over the hypotenuse. Tangent is opposite over adjacent. So the idea is you run through the limerick starting at the angle until you have a match with all 3 values that you're targeting. So if we were looking for this and this, it would be some old horse, and that's what we would use to set up our expression. So let's go ahead and use this in problem 17, which we'll have to pick up in the next video.